Beneath every solid object, every beam of light, and every quiet second passing on a clock, reality is behaving in ways the human mind was never built to see. Particles exist as possibilities. Distant objects share invisible connections. Empty space flickers with hidden activity. And even black holes may slowly fade because of the strange rules of the quantum world. This is not science fiction. It is the foundation beneath atoms, lasers, computers, timekeeping, and perhaps space-time itself. Thank you for spending part of your day or night here. What time is it where you are, and where are you listening from? Leave a comment and let this quiet journey connect viewers across the world. If this kind of deep, relaxing science brings a little wonder to the night, please support the channel with a like, subscribe for more journeys into the unknown, and share this video with someone who enjoys mysteries that remain real. Now, let the familiar world fall away, and step into the quantum mystery behind everything. Long before any instrument isolates a single atom, the quantum world is already present in every quiet surface, every beam of light, every breath of air, and every solid object that seems to rest without movement. Matter appears stable because human senses average over immense numbers of particles, smoothing their restless behavior into familiar shapes. A table seems still, a wall seems continuous, a stone seems complete in itself. Yet beneath that calm appearance, electrons occupy strange allowed states, atoms vibrate, fields fluctuate, and particles exchange energy in exact packets. The ordinary world does not sit above quantum physics as if the two belong to separate realms. The ordinary world is quantum physics, gathered into large patterns that conceal the strangeness of their origin. Quantum mechanics begins as a theory of the very small, but its reach is not small. It governs how atoms hold together, how molecules form, how stars release light, and how matter resists collapse. It shapes the colors of minerals, the chemistry of living cells, the flow of electricity through metals, and the behavior of the semiconductors inside modern machines. Without quantum rules, electrons would not settle into stable structures around atomic nuclei. Chemistry would lose its architecture. Solids would not possess the same strength. Gases would not behave in recognizable ways, and the long chain of physical events leading to planets, oceans, and life would be broken near its beginning. The theory describes a hidden order so deep that nearly everything familiar depends on it, even when nothing in daily experience reveals how unusual that order is. The name quantum points toward a central discovery. Energy does not always change in a perfectly smooth flow. In many physical systems, it comes in distinct portions, like steps on a staircase rather than points along a ramp. An electron bound inside an atom cannot simply possess any energy it pleases. It is limited to certain states. To move from one state to another, it must gain or lose a precise amount of energy. Light can provide that energy through particles called photons, each carrying an amount linked to its frequency. This simple relationship lies beneath a vast range of phenomena. It helps explain why atoms absorb and emit particular colors, why stars display identifying patterns in their spectra, and why carefully chosen frequencies can control matter with extraordinary precision. This deep structure first becomes unavoidable when older physics reaches its limits. Classical physics, built from the work of Newton and others, describes the motion of planets, falling objects, machines, waves, and fluids with remarkable power. In that framework, the universe resembles a great mechanism. Every object has a position and a motion. Every event grows from earlier conditions. With enough information, the future seems predictable in principle. Even when the calculations become impossibly difficult, a thrown stone follows a path determined by its speed, angle, and the forces acting upon it. A planet moves through space according to gravity. A wave spreads through water because one region pushes upon the next. The world appears continuous, definite, and independent of observation. At the scale of atoms and light, this picture begins to fail. Light behaves like a wave when it spreads, interferes, and bends around obstacles. Yet it also behaves like a stream of particles when it transfers energy in concentrated events. Matter creates the same problem from the opposite direction. Electrons behave as particles when they strike a detector at individual points. But they also produce wave-like interference when allowed to travel through carefully arranged experiments. The categories that seem clear in ordinary life no longer remain separate. A thing may not be simply a particle or simply a wave. It follows quantum rules that can resemble either description, depending on how the system is prepared and measured. This is not merely a weakness in language. It reflects something fundamental about the theory. Quantum mechanics does not usually assign a particle one definite path in the same manner as classical physics. Instead, it describes a range of possible outcomes through a mathematical object called the wave function. The wave function evolves in an orderly way, carrying information about what may happen and how likely each result is. When a measurement occurs, however, only one outcome appears. A detector records a particle in one place rather than across a cloud of possibilities. An atom is found in one energy state rather than every allowed state at once. The theory predicts the distribution of these results with astonishing accuracy, but the transition from possibility to observed fact remains one of its deepest puzzles. Probability therefore enters quantum physics in a form unlike ordinary uncertainty. A coin toss seems random because the details of its motion are too difficult to follow. In principle, its result is fixed by the force of the toss, the movement of the air, the shape of the coin, and the surface where it lands. Quantum probability appears more deeply rooted, even when a system is prepared as completely as the theory allows. The outcome of a single measurement may remain unpredictable. Only the probabilities can be known. Repeating the experiment many times reveals a stable pattern. Yet no calculation within standard quantum theory identifies the exact result of the next event. The uncertainty does not simply hide missing information in an obvious classical sense. It belongs to the structure of the description itself. From this uncertainty comes superposition, one of the most famous and most easily misunderstood ideas in science. A quantum system can be represented as a combination of possible states. An electron may occupy a superposition of different energy levels. A particle may carry a superposition linked to different locations or paths. This does not mean that a tiny classical object is secretly jumping between ordinary positions faster than any instrument can follow. It means the system possesses a quantum state for which the classical alternatives do not yet provide a complete description. The possible outcomes remain joined within one mathematical structure until interaction with a measuring device or surrounding environment produces a definite record. The surrounding environment matters because quantum states are fragile. A particle rarely remains perfectly isolated. It interacts with stray light, nearby atoms, thermal motion, and fields. These interactions spread quantum information into the environment through a process called decoherence. Decoherence helps explain why large objects do not visibly remain in superpositions of dramatically different conditions. Their countless particles interact with the world so quickly that delicate quantum relationships become inaccessible. The strange possibilities do not need to vanish through a simple mechanical switch. Instead, they become dispersed across an enormous network of correlations, leaving ordinary reality with the appearance of stable, separate outcomes. That appearance is powerful enough to build civilization. Transistors depend on quantum behavior inside semiconductors. Lasers rely on controlled transitions between atomic energy states. Atomic clocks use the fixed frequencies associated with those transitions to measure time with exceptional precision. Medical imaging, digital communication, navigation systems, solar cells, light-emitting devices, and much of modern computation all rest on quantum principles. The theory does not survive merely because it is philosophically interesting. It survives because experiments return the results it predicts, often with a precision unmatched by any other framework in science. Its influence reaches far beyond laboratories and electronic devices. Quantum physics helps determine how stars shine by governing the interactions and energy states of particles in stellar interiors. It shapes the behavior of dense matter inside white dwarfs and neutron stars. It enters the study of the early universe, where matter and radiation exist under extreme conditions. Near black holes, quantum fields lead to the prediction that horizons may emit faint radiation, allowing even the darkest objects to lose energy over immense spans of time. Across the larger scales, the physics of the smaller scales continues to leave a trace. The deepest mystery is not whether quantum mechanics works. Its success is overwhelming. The mystery is what kind of reality allows it to work so well. The theory offers probabilities, superpositions, fields, amplitudes, and precise rules for prediction. Yet it does not settle every question about what exists between measurements, why one outcome becomes actual, or whether all possible outcomes remain in some broader structure. Different interpretations preserve the same experimental success, while telling very different stories about the hidden nature of the world. Beneath every stable object and every measured moment, the mathematics continues to point toward a reality that is both exact and unresolved, quietly supporting everything while refusing to become fully familiar. For centuries, the physical world appears to obey a calm and intelligible order. Stones fall, planets turn, pendulums swing, and waves spread across water in patterns that can be measured and predicted. The laws of motion describe how forces change movement. The law of gravity joins the path of an apple to the orbit of the moon. Heat, sound, pressure, electricity, and magnetism gradually become parts of a widening system in which nature seems governed by continuous causes. This classical picture does not remove mystery, but it gives mystery a structure. The universe appears to possess definite properties at every moment, whether anyone observes them or not. Objects have positions, velocities, temperatures, and energies. With perfect knowledge of the present and perfect knowledge of the laws, the future seems fixed in principle. Human ignorance may prevent exact prediction, yet nature itself appears to contain no hidden uncertainty. By the end of the 19th century, this framework is so successful that some physicists suspect only details remain unfinished. The great architecture seems nearly complete. Newtonian mechanics governs ordinary motion. Thermodynamics explains energy, work, and heat. Maxwell's equations unite electricity, magnetism, and light into one elegant theory of electromagnetic waves. The scientific world possesses a picture of reality that is powerful, coherent, and deeply persuasive. Then small failures begin to gather at its edges. They do not first appear as dramatic contradictions. They appear as narrow technical problems involving light, heat, atoms, and radiation. Each seems local. Together, they reveal that the old framework is reaching a boundary. One difficulty emerges from the study of hot objects. A heated metal changes colour as its temperature rises, first glowing red, then orange, then pale and bright. Classical physics attempts to explain the distribution of energy across the different frequencies of emitted light. Its equations work at lower frequencies but predict an impossible explosion of energy at higher ones. According to the classical result, A warm object should pour out limitless radiation in the ultraviolet range. Nature does nothing of the kind. The prediction becomes known as the ultraviolet catastrophe, not because any object truly produces such devastation, but because the theory collapses into nonsense. A remedy arrives when Max Planck proposes that energy is exchanged in discrete portions rather than in any arbitrary amount. The proposal is initially a mathematical device, but it opens a crack in the assumption that nature changes only through smooth, continuous steps. Energy may come in units. The continuous world may rest upon something granular. Another failure appears in the photoelectric effect, in which light striking a metal can eject electrons from its surface. Classical wave theory suggests that brighter light should deliver more energy to each electron, regardless of colour, provided it shines long enough. Experiments show a different pattern. Below a certain frequency, no electrons emerge, even when the light is intense. Above that frequency, electrons are released almost at once, and their energy depends mainly on the light's frequency rather than its brightness. Albert Einstein explains the effect by treating light as if it arrives in localized packets of energy. These packets later become known as photons. Light, already established as a wave through interference and diffraction, now reveals a particle-like side. The same entity seems to resist the categories available to classical thought. A third crisis lies within the atom. Classical models struggle to explain why atoms remain stable. If electrons orbit a nucleus like planets around the Sun, then according to electromagnetic theory, they should radiate energy, spiral inward, and collapse. Matter should not last. Atoms also emit and absorb light at sharply defined frequencies, producing spectral lines that act like fingerprints for each element. Classical mechanics offers no natural reason for these exact patterns. Niels Bohr introduces a model in which electrons occupy only certain allowed orbits and exchange energy by jumping between them. The model is incomplete, yet it captures a crucial truth. Atomic energy is quantized. The electron does not move through every possible intermediate state. It appears to pass between permitted levels according to rules that have no classical equivalent. These problems deepen when matter itself begins to display wave-like behavior. Louis de Broglie proposes that particles such as electrons possess wavelengths related to their momentum. Experiments later confirm electron diffraction, showing that electrons can create interference patterns much like light. The particle and the wave no longer stand as separate kinds of physical thing. Light behaves as both. Matter behaves as both. The question is not which description is correct in an absolute sense, but why nature permits each description to appear under different experimental conditions. Classical physics assumes that an object follows one definite path. Quantum experiments refuse to reveal such a path in the expected way. In the double-slit experiment, individual particles travel toward a barrier containing two narrow openings. Each particle strikes a detector at one point, as if it were a tiny object. Yet after many particles arrive, the pattern that accumulates resembles the interference of waves passing through both openings. Even when particles are sent one at a time, the interference pattern slowly forms. Each event is localized, but the distribution of events follows a wave-like rule. Any attempt to determine which opening the particle passes through changes the result. The interference fades, and the system behaves more like a classical stream of particles. The experiment does not simply expose a mechanical trick. It reveals that the way a question is physically asked helps determine which aspect of the system can appear. This does not mean human consciousness commands matter. A measuring device is a physical system. An interaction leaves a record. The mystery lies in the structure of the interaction, not in a private act of awareness. Still, the result is unsettling because the classical separation between observer and observed becomes difficult to preserve. In older physics, Measurement reveals a property that already exists. In quantum physics, measurement participates in defining the outcome that becomes recorded. The old ideal of a world carrying all its properties in fully definite form begins to weaken. Werner Heisenberg gives this limit a precise expression through the uncertainty principle. Certain pairs of quantities, such as position and momentum, cannot both possess arbitrarily sharp values within the same quantum state. The limitation is not merely caused by clumsy instruments. It is built into the mathematical structure of the theory. A state tightly localized in position requires a broad spread of possible momenta. A state with sharply defined momentum must extend across a wider region of space. The uncertainty principle, therefore, does not announce that nature is vague in every way. It describes an exact relationship between what can be simultaneously definite. Quantum mechanics replaces the classical trajectory with a wave function, a mathematical object that evolves according to a precise equation. The wave function does not normally provide one inevitable result for a future measurement. It provides amplitudes from which probabilities can be calculated. The mathematics is orderly, but the observed outcome is not uniquely fixed by that order. This tension creates a new kind of physical law. Between measurements, the quantum state evolves smoothly. At measurement, one result appears from among several possibilities. The theory predicts the statistics with extraordinary reliability, while leaving the status of the unobserved alternatives open to interpretation. Classical determinism does not disappear everywhere. Large systems still follow classical equations with great accuracy because quantum effects average out, lose coherence, or become too small to notice. Planets do not blur across their orbits. Falling objects do not arrive in visibly separated quantum states. The older laws remain valid within their domain, much as a map remains useful without describing every grain of soil. Quantum mechanics does not destroy classical physics. It reveals that classical physics is an approximation emerging from a deeper level. The boundary is therefore not a clean wall between two universes. It is a gradual change in which scale, isolation, interaction, and environmental noise determine what can be observed. The classical world rises from quantum foundations, yet the path from one to the other remains subtle. At the point where 19th century physics seems closest to completion, nature opens into a stranger order. Waves become particles, particles become waves. Energy arrives in steps. Atomic stability depends on forbidden and allowed states. Measurement no longer behaves as a passive glance. The old clockwork universe does not simply break. It becomes the visible surface of a deeper machinery whose rules are less intuitive, more precise, and far more mysterious. At the heart of quantum mechanics lies a change more unsettling than the discovery of hidden particles or unfamiliar waves. The change concerns certainty itself. Classical physics allows uncertainty, but it treats that uncertainty as a weakness in knowledge. A tossed coin appears unpredictable because its exact speed, spin, angle, air resistance, and impact are not fully known. A cloud seems chaotic because too many molecules move at once to track individually. Yet beneath the confusion, every part of the system is assumed to possess definite properties and to follow definite laws. Quantum mechanics offers a different kind of uncertainty, even when a system is prepared as completely as the theory permits. The result of a measurement may not be fixed in advance. The most complete description may provide only a range of possible outcomes and the probability assigned to each one. This does not mean that quantum theory is vague. Its probabilities are among the most precise quantities ever tested in science. The mystery is that precision belongs to the pattern of many events, rather than to the fate of each single event. A radioactive atom may decay within the next moment or remain unchanged for a long time. Quantum theory can calculate the probability of decay over a given interval, and a large collection of identical atoms will follow that prediction with faithfulness. Yet the theory does not identify the exact instant when one atom must decay. Nothing observable within the prepared state marks one atom as the next to change. The event arrives as a definite fact, but the law that precedes it speaks in probabilities. This distinction is easy to blur because ordinary life is filled with statistics. Weather forecasts assign chances to rain. Medical studies estimate risks. Games of chance produce predictable averages across many trials. In each case, probability usually reflects missing information. The atmosphere is too complex to measure perfectly. A human body contains too many variables. A shuffled deck has a definite order that remains unknown. Quantum probability appears more fundamental. The theory does not merely say that the hidden details are difficult to discover. In its standard form, it says that no further detail is available within the quantum state to determine the result. The state is complete, yet the outcome remains open. The mathematical tool that carries this information is the wave function. It does not describe a physical wave in the simple manner of water rising and falling across a pond. It assigns complex amplitudes to possible configurations of a system. These amplitudes can combine, reinforce, and cancel one another. Their squared magnitudes produce the probabilities of measurement outcomes. The rule is exact, but its meaning is subtle. Before measurement, the wave function may include several alternatives at once. After measurement, one alternative becomes the recorded result. The other possibilities no longer appear in that observation. The theory predicts how often each result should occur across repeated trials, yet it does not plainly explain why one possibility becomes actual in a particular case. The double-slit experiment reveals this structure with clarity. A source sends particles toward two openings, and a detector records where they arrive. If the apparatus does not reveal which slit each particle uses, the possible paths contribute amplitudes that interfere. Some regions of the detector become more likely, while others become nearly forbidden. The final pattern is not the sum of two particle streams. It is shaped by the interaction of possibilities. When the apparatus records which path is taken, the interference disappears. The probabilities change because the physical arrangement has changed what alternatives remain coherent. The deeper point is that quantum probabilities depend on the full structure of possible processes, including which distinctions can become part of a record. Probability in this setting behaves less like ignorance about a hidden route and more like a rule governing how unrealized alternatives contribute to what may occur. The randomness of individual results does not create disorder at every scale. Quantum systems produce stable statistical laws. An electron prepared repeatedly in the same state may yield different outcomes in separate measurements, but the long sequence settles into a precise distribution. The unpredictable event and the predictable pattern exist together. This union allows quantum mechanics to support both uncertainty and technological control. Engineers cannot demand one particular spontaneous event, but they can design systems whose collective behavior follows reliable quantum rules, lasers, semiconductors, atomic clocks. And detectors all depend on this statistical regularity. The theory's power does not come from removing chance. It comes from describing chance with extraordinary structure. Albert Einstein resists the idea that probability marks the final level of physical law. His concern is not that the equations fail. He recognizes their success. The concern is that the theory may be incomplete, offering statistics because it omits deeper variables that determine each outcome. In this view, quantum randomness resembles the apparent randomness of a coin, though the hidden causes may be far more subtle. Other physicists accept that the probabilistic description is fundamental, or at least that science should not claim properties that no possible experiment can reveal. The disagreement grows into one of the central debates of modern physics. It asks whether nature truly chooses among possibilities, or whether the appearance of choice hides a deeper deterministic order. Later experiments place severe limits on simple hidden variable explanations. Tests inspired by the work of John Bell examine correlations between entangled particles. The results agree with quantum mechanics and conflict with any class of theories in which particles carry predetermined local instructions independent of distant measurement settings. This does not prove that every imaginable deeper theory is impossible. It does show that any such theory cannot preserve all the familiar assumptions of classical reality. Locality, predetermined properties, and independent measurement choices cannot all remain untouched. The probabilistic structure is therefore not easily dismissed as an incomplete accounting of ordinary hidden facts. Nature's correlations follow rules stranger than classical ignorance can explain. Even so, the word randomness may conceal as much as it reveals. Quantum theory predicts probabilities, but different interpretations describe their origin in different ways. In one family of views, measurement causes the quantum state to collapse unpredictably into a single result. In another, the wave function never collapses, and each result continues within separate branches of a larger reality. In still others, unseen variables guide particles along definite paths while the wave function shapes their motion in a non-local way. Some approaches treat the wave function as information about possible experiences rather than as a direct picture of an independent physical object. These interpretations often agree on experimental predictions while disagreeing sharply about what the mathematics represents. The same probabilities can therefore sit within very different visions of reality. The debate points toward an unresolved boundary between calculation and existence. Quantum mechanics tells science how to assign probabilities with unmatched success. It does not force one universally accepted answer about what is probable, what makes one event occur, or whether all alternatives remain real in some extended sense. The theory is complete enough to build devices and predict experiments, yet open enough to support incompatible accounts of the world beneath those predictions. This tension becomes especially clear when probability meets causation. In classical thought, every event follows from prior conditions through a continuous chain. Quantum events still obey conservation laws and constraints, but the exact outcome may not be selected by any known prior fact. A photon reaching a half-reflective mirror may be transmitted or reflected. The apparatus can be made identical for every trial. The probabilities can be calculated exactly. Still, the next event remains uncertain. The cause seems to determine the menu of possibilities and their weights, but not the single result. Nature appears lawful without being predetermined. This is not chaos. It is a different form of order, at large scales. Countless quantum events combine into the stable world of ordinary experience. Random microscopic changes average into smooth pressures, steady currents, familiar temperatures, and predictable material properties. Yet the underlying openness never entirely disappears. It can be amplified. A single quantum event may trigger a detector, start a chemical reaction, alter a biological molecule, or become part of a macroscopic record. The uncertain microscopic outcome can enter history as an irreversible fact. The universe therefore contains a curious movement from possibility to actuality, repeated without pause in atoms, fields, stars, instruments, and living systems. Quantum mechanics maps that movement with precision, but it leaves its deepest meaning unsettled. The clockwork universe once promises that the future already exists in the present, hidden only by ignorance. Quantum theory replaces that promise with a quieter and stranger picture. The present contains a structured field of possibilities. The future is constrained, weighted, and lawful, yet not always fixed in a single line. What emerges is not a universe without order, but a universe in which order itself is written in probabilities, and where certainty appears only after one possibility has become part of the world. Quantum mechanics becomes most mysterious at the moment when a possibility becomes a fact. Before measurement, the theory describes a system through a wave function containing several potential outcomes. After measurement, an instrument records one result, a detector clicks in one place, an atom is found in one energy state, a photon follows one channel rather than another. The transition seems ordinary because measurements happen constantly, yet the theory treats the two sides of that transition in profoundly different ways. Between measurements, the wave function evolves smoothly and predictably according to a precise equation. During measurement, the usual description appears to give way to a sudden selection. The many possible outcomes reduce to one observed event. This contrast is known as the measurement problem, and it reaches into the foundation of what quantum theory claims reality to be. The problem does not arise because instruments are crude. Quantum experiments prepare nearly identical particles and register individual events with extraordinary control. Still, the theory does not provide a universally accepted account of how one definite outcome emerges. It tells science the probability of each result, and those probabilities agree with experiment. What remains unclear is whether the wave function truly collapses, whether collapse is only an update in knowledge, whether every outcome continues in some broader reality, or whether another hidden process creates the appearance of selection. In classical physics, measurement seems conceptually simple. A planet possesses a position before a telescope records it. A pendulum has a speed before a clock measures its motion. The act of observation may disturb the system slightly, but the measured property is assumed to exist independently. Quantum mechanics weakens this picture. Some properties do not appear to possess definite values in the quantum state before the relevant measurement. The theory may assign a superposition of possible values instead. Measurement does not merely uncover a hidden number. It produces a record in which one value becomes definite. This is not a statement that human awareness creates the world. A measuring device is made of matter and follows physical laws. The difficulty is more precise. The theory contains no obvious boundary explaining why interaction with one physical system counts as ordinary quantum evolution, while interaction with another counts as a measurement yielding a single result. Consider a particle prepared in a superposition of two paths. If the paths remain isolated from the environment, their amplitudes may later recombine and create interference. The interference shows that the alternatives have not behaved like ordinary mutually exclusive routes. Both have contributed to the final probabilities. If a detector is placed along the paths, the detector becomes correlated with them. One state of the detector corresponds to the first path, and another corresponds to the second. Quantum mechanics then describes not a particle with one chosen route, but a larger entangled state containing both particle and detector possibilities. The mathematical evolution alone seems to preserve the superposition by spreading it into the apparatus. Yet experience reveals one detector reading, not a visible combination of incompatible readings. The question simply moves outward. If the detector is included in the quantum description, what selects its final state? The same question can include the laboratory, the environment, and any observer who later reads the result. Each interaction carries information farther outward, but the formalism does not plainly identify where possibility ends and actuality begins. Early formulations often place a practical division between the microscopic quantum system and the classical measuring apparatus. This division works well for calculation, but it leaves the boundary conceptually uncertain. A detector is built from atoms, And those atoms are quantum systems. No obvious size or complexity marks the exact point where quantum evolution must stop and classical definiteness must begin. The boundary can be shifted without changing experimental predictions, suggesting that the division may describe a method rather than a fundamental feature of nature. Decoherence provides an essential part of the modern explanation. When a quantum system interacts with its environment, information about its alternatives becomes dispersed across countless surrounding degrees of freedom. Air molecules scatter from it. Thermal radiation carries traces away. Internal vibrations become correlated with the system. These interactions rapidly suppress observable interference between different macroscopic alternatives. The system begins to behave as though it belongs to a statistical mixture of classical possibilities rather than a coherent superposition. Decoherence explains why fragile quantum effects are difficult to maintain and why large objects appear definite. It also identifies stable states that survive environmental interaction and form classical records. Yet decoherence does not, by itself, explain why one outcome is experienced while the others are not. It transforms an accessible superposition into an effectively inaccessible web of correlations. The alternatives no longer interfere in practice, but the full quantum state may still contain them. The appearance of collapse emerges, while the existence of a single actual result remains an interpretive question. Some approaches accept collapse as a fundamental event. In these views, the wave function evolves smoothly until measurement, then changes randomly into one outcome according to quantum probabilities. This offers a direct account of definite results, but raises further questions. What counts as a measurement? And does collapse have an observable mechanism? Modified theories attempt to answer by proposing spontaneous collapse that becomes more likely as systems grow larger. Such models seek a real boundary between microscopic superposition and macroscopic definiteness, and experiments continue to test how such collapse could operate. Another interpretation removes collapse entirely. The wave function always evolves according to the same smooth equation. During measurement, system, apparatus, and observer become entangled. Different outcomes persist in separate branches that no longer interfere. Each branch contains a version of the measuring process with one definite record. From within a branch, the result appears random because no observer knows which future branch will contain that experience. This many branches picture preserves the universal quantum equation, but it carries an immense implication. All allowed outcomes continue in a wider reality. The mystery shifts from collapse to the meaning of branching, probability, and personal continuity across the expanding structure. Other interpretations place definite particles beneath the wave function. In pilot wave theories, particles always possess actual positions and follow trajectories guided by a quantum wave. Measurement reveals the configuration reached by those trajectories, while the guiding wave accounts for interference and entanglement. This restores a form of determinism, but the guidance is non-local. The behavior of one part of an entangled system can depend on the configuration of another part across distance. The theory shows that definite outcomes are possible without collapse, though at the cost of abandoning a simple classical picture of local influence. Still, other views treat the wave function less as a physical object and more as a tool for organizing expectations about future experiences or records. In such approaches, collapse may resemble the updating of information when a result becomes known. This clarifies why probabilities change after measurement, but leaves open what underlying reality produces the event being learned. Each interpretation solves one difficulty by making another feature of reality more unusual. The measurement problem therefore persists not because quantum mechanics lacks predictive success, but because several incompatible pictures reproduce that success. Experiments establish the probabilities and correlations. They do not yet choose a single meaning for the formalism. The issue sharpens as laboratories place larger molecules, electrical currents, and mechanical resonators into states that reveal superposition or entanglement. The border of the quantum world continues to move outward. No experiment has found a simple scale at which quantum rules fail and classical reality begins. Instead, isolation and environmental interaction determine how long coherence can survive. The familiar world appears less like a separate classical domain and more like a quantum world whose alternatives have become deeply entangled with their surroundings. Every measurement leaves a trace. A microscopic interaction triggers amplification. A detector changes state. Electrical signals move through circuits. Information spreads into memory, light, heat, and the environment. The result becomes effectively irreversible because reversing every correlation would require control over an impossible number of details. In this way, a fleeting quantum possibility becomes a durable historical fact. Yet the equations that describe the process still permit several stories about what has happened. Collapse, branching, hidden trajectories, and informational updating all stand behind the same visible record. At the instant when the detector settles, reality appears to choose clarity. The theory predicts the odds of that clarity with extraordinary precision. It remains silent, or divided into interpretations, about why this fact exists instead of another. The measurement problem is therefore not a minor gap at the edge of quantum mechanics. It is the place where mathematics meets experience, where possibility becomes memory, and where the deepest physical theory still hesitates before the simplest statement that something has happened. Superposition begins with a simple mathematical statement and opens into one of the deepest puzzles in physics. A quantum system can be described as a combination of several possible states, each carrying an amplitude that helps determine the probability of a future measurement. The word combination is easy to hear and difficult to understand. It does not mean that a particle is merely switching rapidly between ordinary conditions, nor does it always mean that several familiar realities sit side by side in the way large objects do. A superposition is a single quantum state whose structure includes more than one possible result. The alternatives remain connected through their phases, allowing them to interfere. That ability to interfere is what separates a true superposition from a simple lack of knowledge. If a hidden coin already lies either heads or tails beneath a cup, ignorance produces uncertainty, but no interference in a quantum superposition. The possibilities can combine before measurement, strengthening some outcomes and cancelling others. The system behaves as though the alternatives remain parts of one unresolved physical description. This structure appears clearly in the behavior of an electron inside an atom. The electron may occupy a superposition of energy states. When carefully controlled light interacts with it, the amplitudes associated with those states evolve in a predictable rhythm. The electron is not well described as secretly choosing one energy and hiding the answer. Its later behavior depends on the relation between the components of the superposition. A well-timed pulse can make the alternatives reinforce or oppose one another, allowing physicists to control the final probability with precision. Atomic clocks use this coherence to compare an atom against an electromagnetic frequency. Quantum computers attempt to use the same principle in qubits, where different logical possibilities are held within one state and manipulated through interference. The power lies not in storing several ordinary answers at once, but in shaping amplitude so that useful outcomes become more likely while unwanted ones are suppressed. Position creates an even more unsettling example. A particle passing through two narrow openings can be placed in a state that includes both possible paths. If no interaction reveals the route, the path amplitudes later recombine and form an interference pattern. Each detection still occurs at one location, but the pattern formed by many detections depends on both openings. Closing either slit changes the distribution. Recording which path is taken destroys the interference. The evidence therefore does not support the idea that the particle simply follows one unknown classical path while the other remains irrelevant. The unrealized alternative has measurable consequences as long as coherence survives. It participates in the probabilities of what becomes real. Language strains at this point. Saying that the particle goes through both openings sounds as though a tiny bead splits into two visible pieces. Saying that it goes through neither fails to explain interference. Saying that it goes through one unknown opening returns to a classical picture that experiments can exclude under appropriate conditions. Quantum theory avoids choosing among these images. It provides the state, calculates the amplitudes, and predicts the pattern. The mathematics is clear even when the picture remains uncertain. Superposition may therefore mark not a bizarre motion within ordinary space, but a sign that ordinary categories are incomplete. Position, path, and even energy may become definite only in relation to a particular kind of interaction. The state before that interaction belongs to a broader space of possibilities called Hilbert space, whose geometry differs from the physical space of everyday objects. Vectors in this abstract space represent quantum states. Adding them creates superpositions. Their relative phases determine interference. Measurement connects this hidden geometry to the definite outcomes recorded in laboratories. This system evolves through the abstract space according to exact rules, while experience reveals only selected results. This gap between the smooth motion of the state and the singular nature of an observed event gives superposition much of its mystery. The famous thought experiment involving a cat is designed to expose the difficulty of extending this logic to large objects. A microscopic quantum event is linked to a mechanism that determines whether a cat lives or dies. If the quantum state includes both decay and no decay, ordinary quantum evolution seems to produce a combined state containing both macroscopic outcomes. Yet no observation reveals a blurred animal occupying life and death as visible conditions. The thought experiment is not a proposal for creating a supernatural creature. It is a challenge to the theory's boundary. If atoms follow quantum rules and large objects are made of atoms, where does superposition stop? The question cannot be answered merely by saying that large objects are classical, because classical behavior must somehow emerge from quantum ingredients. Decoherence supplies much of that emergence. A macroscopic object interacts constantly with air, light, heat, and its own internal degrees of freedom. Each interaction carries away information about the object's state. The alternatives become entangled with different states of the environment. Their relative phases remain part of the total quantum description, but they become practically impossible to track or recombine. Interference between macroscopically different possibilities disappears with extraordinary speed. The object then behaves as though it occupies one member of a classical statistical mixture. Decoherence explains why tables do not visibly spread across rooms and why cats do not reveal interference between life and death. It also shows that the distinction between quantum and classical behavior depends less on size alone than on isolation, control, and environmental coupling. Large systems can display quantum effects when protected carefully, while tiny systems can lose coherence almost immediately when exposed to noise. Laboratories now create superpositions in molecules far larger than single atoms, in electrical currents flowing in opposite directions, and in small mechanical devices whose collective motion enters a quantum state. These achievements extend quantum behavior towards scales once assumed to be permanently classical. They do not make ordinary objects mysteriously dissolve. They reveal that the underlying rule remains quantum even when environmental interaction usually hides it. The practical challenge is to preserve coherence long enough for the different components of a state to interfere. Cooling reduces thermal disturbance. Vacuum chambers remove collisions with air. Electromagnetic shielding limits unwanted fields. Precision control keeps the phases aligned. Every success pushes the visible boundary outward and makes the classical world appear less fundamental. Still, decoherence does not fully settle what exists during superposition. It explains why alternatives stop interfering locally and why stable records emerge, but it does not uniquely select one outcome from the complete quantum state. Different interpretations therefore assign different meanings to the same mathematics. Collapse theories say that superpositions are real but unstable, eventually reducing to one state through a physical process. Many worlds approaches say that all components remain in a universal wave function, with observers becoming correlated to different outcomes. Pilot wave theories give particles definite configurations while the guiding wave passes through the full space of possibilities. Informational interpretations treat the state as a representation of expectations rather than a direct portrait of matter. The experiments confirm the interference and the probabilities, but the unseen condition between preparation and measurement remains open to interpretation. Superposition also challenges the idea that properties belong to objects in isolation. A quantum state may be defined only relative to an experimental arrangement. A particle can have a sharp energy while its position remains spread. It can have a sharp position while its momentum becomes uncertain. Different measurements reveal different aspects, and no single classical description contains them all at once. This does not make reality dependent on imagination or private awareness. The measuring arrangement is physical. It determines which interaction occurs and which record can form. What changes is the assumption that every measurable property must already possess a hidden definite value before that interaction. Quantum mechanics replaces that assumption with a state containing structured possibilities. The unseen state is therefore not a cloud of pure confusion. It has exact form, evolves by exact equations, and produces repeatable interference. Its mystery comes from being more precise than any ordinary picture while resisting translation into ordinary terms. Superposition shows that possibility can possess physical structure before an outcome becomes fact. The alternatives are not merely stories about ignorance, because they influence the pattern of what later appears. Yet they are not visible worlds in the everyday sense. Because measurement yields one result and environmental interaction hides their coherence. Between those two facts lies a quiet region where quantum reality remains mathematically clear and conceptually unresolved, holding several futures together until the world records one of them. Time seems to pass with perfect simplicity. A second follows another second. Clocks divide the flow into equal intervals, and daily life proceeds as though duration were an invisible background shared by everything. Yet the most accurate clocks do not depend on swinging hands, falling weights, or the turning of Earth. They depend on quantum transitions inside atoms, where energy changes only in exact steps. In these transitions, the quiet strangeness of the microscopic world becomes a standard for measuring one of the most familiar features of existence. An atomic clock begins with the fact that electrons bound within an atom can occupy only certain allowed energy states. They cannot rest at arbitrary points between them. To move from one state to another, an electron must absorb or release an exact amount of energy. That energy can be carried by electromagnetic radiation at a precise frequency. When the radiation matches the energy difference between two atomic states, the atom responds strongly. This matching condition is called resonance, because atoms of the same kind share the same internal structure. Their resonant frequencies provide remarkably stable references. A pendulum can change with temperature, wear, or gravity. The rotation of Earth can speed up or slow down slightly. An atomic transition, once external disturbances are controlled, offers a pattern rooted in the laws of quantum physics. The modern definition of the second uses a transition in the cesium atom. The clock does not listen to a tiny mechanical ticking inside the atom. It generates microwaves and adjusts their frequency until they produce the strongest response in a collection of cesium atoms. The microwave oscillations are then counted. A fixed number of these cycles defines 1 second. The process turns a quantum energy difference into a universal rhythm. Any laboratory that prepares the same atoms, controls the same conditions, and corrects the same disturbances should recover the same reference. Timekeeping becomes less dependent on a particular machine and more dependent on a reproducible feature of matter. This precision enters ordinary life quietly. Navigation satellites carry atomic clocks because location on Earth is calculated from the travel time of radio signals. A signal moving at the speed of light covers a great distance in a tiny fraction of a second. A small error in timing becomes a much larger error in position. Receivers compare signals from several satellites, each broadcasting when the signal was sent and where the satellite was located. From the differences in arrival time, the receiver determines distance and then position. The map appearing on a screen therefore depends on clocks in orbit remaining synchronized with extraordinary care. The quantum transition inside an atom becomes part of a route through a city, the coordination of communication networks, the movement of aircraft, the operation of financial systems, and the measurement of Earth itself. Atomic clocks also reveal that time is not a single universal current. Einstein's theory of relativity shows that motion and gravity affect the rate at which clocks run. A clock moving rapidly relative to another clock accumulates a different amount of time. A clock deeper in a gravitational field runs more slowly than one farther away. These effects are small in ordinary conditions, but atomic clocks are precise enough to measure them. Satellite clocks experience weaker gravity than clocks on Earth's surface, which tends to make them run faster. Their orbital motion tends to make them run slower. Both effects must be corrected for navigation systems to remain accurate. Without relativity, even quantum precision would lead the system away from the correct position. The clock therefore becomes a meeting point between two great theories. Quantum mechanics supplies the atomic rhythm. Relativity explains how that rhythm changes with motion and gravity. Newer optical atomic clocks extend this sensitivity much further. Instead of using microwave frequencies, they use visible or near-visible light. Optical waves oscillate far more rapidly than microwaves, providing many more cycles within the same interval. More cycles act like finer marks on a ruler, allowing smaller differences in time to be resolved. These clocks often use atoms such as strontium, ytterbium, or aluminum ions. Lasers are tuned to extremely narrow atomic transitions, and the atoms are cooled and isolated so that motion, collisions, electric fields, and magnetic fields do not blur the resonance. In some designs, many atoms are trapped in a pattern of laser light called an optical lattice. The lattice holds the atoms nearly still while allowing their internal quantum states to serve as a shared reference. In others, a single charged atom is confined by electromagnetic fields and studied with exquisite control. The machinery surrounding the atoms can fill a laboratory, yet the standard itself lies in a tiny energy difference. To make such a clock work, physicists place atoms into a carefully controlled quantum superposition of two energy states. The relative phase between those components evolves like a pendulum. Though nothing swings through ordinary space, a laser probes that evolution. If the laser frequency matches the atomic transition, the phase relationship develops in a predictable way. Repeated measurements allow the laser to be locked to the atom. The clock then counts the oscillations of the stabilized light. Superposition, often presented as a distant mystery, becomes the working heart of a practical instrument. The clock is precise because quantum possibilities remain coherent long enough to form an exact comparison. That precision turns timekeeping into sensing. General relativity predicts that a difference in height produces a difference in the rate of time because gravity becomes slightly weaker farther from Earth's centre. Optical clocks can detect this change across remarkably small differences in elevation. One clock placed higher than another accumulates time at a slightly faster rate. The difference is tiny, but it can be measured when the clocks are sufficiently stable. A clock can therefore act as a probe of gravitational potential. It does not merely state the time, it senses where it is within the shape of Earth's gravitational field. This creates the possibility of relativistic geodesy, in which networks of clocks help map changes in height, underground density, water movement, volcanic processes, and the slow deformation of the crust. Time itself becomes a way of measuring the planet. The deeper sensitivity also exposes the limits of isolation. Every influence shifts the atomic frequency by some amount. Thermal radiation from the walls of a chamber can alter energy levels. Magnetic fields can split or displace them. Collisions between atoms can create subtle changes. Motion causes frequency shifts. Even the laser used to interrogate the atom can disturb the transition being measured. Building a better clock, therefore, means identifying and controlling an expanding catalogue of effects. Precision does not remove complexity. It reveals smaller layers of it. Once one disturbance is reduced, another becomes visible. The approach toward perfect timekeeping becomes an approach toward the full physical environment surrounding the atom. At extreme precision, the meaning of a clock also becomes less obvious. Two clocks separated in height do not agree, because relativity says no single universal rate belongs to both locations. Synchronization requires a convention and a model of the gravitational field. A global timescale is assembled from many clocks, comparisons, corrections, and agreed procedures. The second remains defined through an atomic transition, but its realization across Earth depends on the structure of space-time. Timekeeping is therefore both local and collective. Each atom follows its own proper time along its path, while civilization constructs shared time by linking countless paths together. Atomic clocks may also test whether the laws of physics remain constant. Different types of atoms respond differently to possible changes in fundamental quantities. By comparing clocks based on separate transitions over long periods, physicists can search for tiny drifts that might signal physics beyond established theories. Clocks can test relativity, constrain unknown interactions, and search for subtle effects associated with dark matter or other hypothetical fields. No confirmed discovery of that kind is required for the clocks to be valuable. Their importance lies in making previously unreachable questions measurable. A device built to count seconds becomes an instrument for asking whether the foundations of nature remain unchanged. The mystery grows quieter as the precision increases. An atomic clock appears to divide time into regular units, yet it reveals that time does not flow identically everywhere. Its quantum rhythm is universal in one sense, because identical atoms share the same transition. Its measured rate is local in another, because gravity and motion shape the passage of duration. Beneath every synchronized network lies a negotiation between quantum states and curved space-time. The second seems simple only after these layers have been controlled, compared, and translated into a common standard. In the narrow resonance of an atom, time becomes both more exact and less absolute, measured through a microscopic transition that opens onto the geometry of the universe. Ordinary light appears effortless, a lamp glows, sunlight crosses a room, and a flame throws shifting colour into the air. Yet this familiar light is usually disordered. Its atoms emit photons at many moments, in many directions, with many frequencies and phases. The result can be bright, warm, and useful, but it lacks the deep coordination that makes a laser different. Laser light is organized light. Its photons share nearly the same frequency, move in nearly the same direction, and maintain a stable relationship between their waves. That coherence allows a beam to remain narrow over long distances, to carry information with precision, and to measure changes far smaller than ordinary instruments can detect. Behind that order lies a distinctly quantum process. The word laser comes from light amplification by stimulated emission of radiation. Each part of the name points toward the mechanism. Atoms and molecules contain electrons arranged in allowed energy states. An electron in a higher state can fall to a lower one and release a photon whose energy matches the difference between those states. This spontaneous emission occurs naturally, but the emitted photon leaves at an unpredictable time and in an unpredictable direction. A collection of excited atoms therefore produces light whose phases are unrelated. Stimulated emission changes that. When a photon of the right energy passes an excited atom, it can trigger the electron to fall, causing the atom to emit a second photon. The new photon matches the first in frequency, direction, phase, and polarization. One photon becomes two closely coordinated photons. Those photons can stimulate more atoms, producing a growing cascade of organized light. This is not the copying of an arbitrary quantum state, which quantum theory forbids in general. It is the amplification of a particular mode of the electromagnetic field through controlled transitions. A laser device creates the conditions for this amplification. A material called the gain medium contains atoms, molecules, or charge carriers capable of emitting the desired light. Energy is supplied through electricity, another light source, or a chemical process, raising many of the particles into excited states. This preparation is called pumping. Under ordinary conditions, more particles occupy lower energy states than higher ones. For stimulated emission to dominate absorption, the balance must be reversed so that enough particles remain excited. This condition is known as population inversion. It is not a natural equilibrium. It must be created and maintained, like holding water above its resting level before allowing it to flow downward. Once the gain medium is prepared, mirrors placed around it form an optical cavity. Photons traveling along the cavity bounce repeatedly through the excited material, stimulating further emission. The distance between the mirrors favors certain standing wave patterns, selecting narrow frequencies that fit the cavity. One mirror reflects almost all the light. The other allows a small fraction to escape. That escaping fraction becomes the beam. The cavity does more than increase brightness. It filters and organizes the field, favoring photons that match its permitted modes, while other directions and frequencies are lost. The result is a stream of light with a degree of order rarely found in nature. Coherence is central to that order. Two waves are coherent when the relationship between their phases remains stable. If their peaks and troughs move together, they can reinforce one another. If a peak meets a trough, they can cancel. Ordinary light from a bulb contains many independent waves whose phase relationships change rapidly, so its interference is washed out. Laser light preserves phase over much longer distances and times. This makes interference visible and controllable. When a laser beam is divided and later recombined, tiny differences in the paths shift the phases and change the resulting brightness. A movement far smaller than the wavelength of the light can alter the interference signal. Distance is converted into phase, and phase can be measured with exceptional sensitivity. This principle makes interferometry one of the laser's most powerful uses. A beam splitter sends light along separate paths. Mirrors return the beams to a detector, where they recombine. If the paths have equal optical length, The waves may cancel or reinforce according to their chosen phase relation. A small movement of a mirror changes one path and shifts the pattern. The instrument does not need to observe the movement directly. It reads the change in interference. With stable lasers, isolated mirrors, and careful control of vibration, interferometers can measure distortions much smaller than an atomic nucleus. Such sensitivity opens a path from laboratory optics to the motion of space-time itself. Lasers also transform communication. Information can be encoded in the intensity, phase, frequency, or polarization of light. Because optical frequencies are extremely high, a light beam can carry rapid streams of data. Glass fibers guide the beam across continents and beneath oceans, while preserving much of its structure. The messages moving through these fibers depend on quantum transitions in semiconductor lasers, where electrons and vacancies called holes recombine and release photons. Mirrors and layered materials select the allowed optical modes. A device small enough to fit inside a communication system produces coherent light that joins distant networks. The same underlying process also appears in barcode scanners, printers, optical storage, surveying equipment, industrial cutting, and medical procedures. Each application uses a different combination of wavelength, power, pulse length, and coherence, but all begin with controlled quantum emission. A laser can also be made to produce extremely short pulses. In such systems, many frequencies are locked together so that their waves briefly align, concentrating energy into a narrow interval. These pulses can last for only a tiny fraction of a second. Their brevity allows physicists to observe fast molecular changes, the motion of electrons, and the breaking and forming of chemical bonds. A process, once blurred into an average, can be separated into stages. The laser becomes a clock for events too rapid for ordinary timing, and a ruler for distances too small for ordinary measurement. In precision science, the stability of a laser matters as much as its brightness. A perfect single-frequency wave would continue forever, with an exactly defined rhythm. Real lasers have a finite line width, meaning their frequency occupies a narrow range. Temperature changes, mechanical vibration, electrical noise, and quantum fluctuations disturb the cavity and broaden that range. Physicists reduce these effects by placing cavities in vacuum, controlling their temperature, choosing materials that expand very little, and suspending components from vibrations. The laser frequency can then be compared with an atomic transition and corrected continuously. This creates a light source whose oscillations remain stable enough to drive optical clocks and detect minute changes in distance. Yet even the quietest laser contains quantum noise. Light arrives in discrete photons, and their detection follows statistical fluctuations. The number reaching a detector during a given interval is not perfectly fixed. These variations create shot noise, a fundamental limit in many measurements. Quantum mechanics, which makes the laser possible, also restricts its precision. The restriction can sometimes be reshaped. In squeezed light, uncertainty is reduced in one property of the field while increasing in another, consistent with the uncertainty principle. An interferometer designed to measure one chosen property can use this redistribution to improve sensitivity. Quantum states of light therefore become tools for pushing instruments beyond the limits of ordinary laser beams. The laser reveals a recurring pattern in quantum technology. A strange microscopic rule becomes useful when it is isolated, repeated, and controlled. Stimulated emission is not visible in daily experience, yet it can coordinate vast numbers of photons into one beam. Superposition and phase are abstract ideas, yet they determine whether waves reinforce or disappear. Quantum fluctuations seem like unavoidable noise, yet their distribution can be engineered. The theory does not become less mysterious when it becomes practical. Its mystery is built into the instrument. Every coherent beam carries evidence that atoms exchange energy in discrete steps, and that light behaves as both a field and a stream of quanta. The beam's smooth appearance hides the individual events that sustain it. The laser is therefore more than an intense source of light. It is a bridge between the invisible rules of atoms and the measurable structure of the world. It reads distance through phase, time through frequency, matter through absorption, and motion through shifting wavelengths. It can cut metal because its energy is concentrated, transmit information because its oscillations are controlled, and test fundamental physics because its coherence preserves tiny differences. As its stability improves, smaller changes become visible. A mirror moves by less than the width of a proton. An atom reveals a subtle shift in energy. A distant collision disturbs the geometry of space. Organized light becomes a way for the universe to measure itself, using quantum order to expose motions and structures that would otherwise remain silent. Space-time is not a rigid stage upon which the universe performs. According to general relativity, it bends around matter and energy, guiding planets, stars, and light along paths shaped by gravity. When massive objects accelerate, their motion does not remain confined to the region around them. It sends disturbances outward through the geometry itself. These disturbances are gravitational waves, ripples in space-time that travel at the speed of light. They are not waves moving through space in the way sound moves through air. They are changes in the distances and intervals that define space-time. As one passes, the separation between freely falling objects stretches in one direction and contracts in another, then reverses in a rhythm carried across the cosmos. The effect is extraordinarily small by the time it reaches Earth. A collision between black holes can release immense power, yet the arriving wave may change several kilometers by less than the width of a proton. Detecting it requires an instrument able to measure almost nothing beneath ground motion, machinery, thermal movement, and quantum fluctuations of light. This is the task of laser interferometers such as the twin observatories of LIGO. Each observatory is built around two long arms placed at right angles. A highly stable laser enters a beam splitter, which sends part of the light down one arm and part down the other. Mirrors at the ends return the beams. When the light recombines, the waves are arranged so that they nearly cancel. Under ideal conditions, little light reaches the output detector. The instrument is balanced on darkness. If a gravitational wave passes through, it changes the lengths of the arms in opposite ways. One becomes slightly longer, while the other becomes slightly shorter. The returning light then carries a small phase difference. The cancellation becomes incomplete, and a faint signal appears. The detector reads not the wave directly, but the light that escapes from what should have been darkness. The signal is identified not by one bright flash, but by a characteristic pattern unfolding through time. Models of orbiting compact objects predict how the frequency and amplitude should rise as the bodies draw together. Data analysis compares the detector output with large families of possible waveforms, searching for a matching structure within the noise. This method can uncover signals too weak to stand out by eye. It also means that detection depends on theory, computation, and instrument working together. The wave is not simply seen. It is recognized through the precise shape that gravity predicts. The basic idea is simple, but the measurement demands extraordinary control. The mirrors hang from elaborate suspensions that isolate them from ground motion. Vacuum tubes remove air that would scatter the laser, while active systems track vibrations from earthquakes, wind, traffic, and human activity. The arms extend for several kilometers, not because the gravitational wave is large, but because a longer distance creates a larger measurable change. Light also bounces many times between the mirrors, effectively increasing the path and allowing the wave to leave a stronger phase shift. The observatory becomes a machine built to preserve one delicate comparison against nearly every form of disturbance on Earth. At the heart of the measurement lies quantum light. The laser produces a coherent electromagnetic field whose phase can be tracked with immense precision. Yet the beam is made of photons, and their arrival at the detector is not perfectly smooth. Even a stable beam contains fluctuations in the number detected during a given interval. This shot noise limits the measurement at higher frequencies. Increasing laser power reduces relative counting uncertainty, but photons striking a mirror transfer momentum. Fluctuations in their number produce radiation pressure noise, which can move the mirrors at lower frequencies. More light improves one part of the measurement while disturbing another. The uncertainty does not come merely from imperfect engineering. It grows from the quantum nature of the field used to probe space-time. Physicists reshape this limit with squeezed light. In an ordinary quantum state of light, uncertainty is distributed between two related properties of the electromagnetic field. The uncertainty principle prevents both from becoming arbitrarily precise at once, but it allows uncertainty to be reduced in one while increasing in the other. A squeezed state is prepared so that the property most important to the measurement becomes quieter. Injected into the interferometer, this specially controlled vacuum state reduces quantum noise in the output. The improvement does not violate the uncertainty principle. It redirects unavoidable uncertainty into a form that matters less. By engineering vacuum fluctuations, the observatory gains a clearer view of distant events. The first direct detection of gravitational waves arrives from two black holes spiraling together. For a long time, they orbit one another, losing energy through gravitational radiation and drawing closer. Their motion accelerates. The frequency and strength of the waves increase, creating a rising signal known as a chirp. In the final moments, the horizons merge. The newly formed black hole vibrates and settles into a stable shape, releasing the last part of the signal as a fading ring. The entire pattern is encoded in a brief distortion of the interferometer arms. From that waveform, physicists infer the masses of the black holes, their rotation, their distance, and the nature of the collision. The event is known through the motion it imprints on space-time. Gravitational wave astronomy therefore opens a sense that earlier observatories do not possess. Telescopes collect electromagnetic radiation, including radio waves, visible light, X-rays, and gamma rays. Those signals reveal immense detail, but matter can absorb, scatter, or block them. Gravitational waves interact weakly with matter and travel outward with little disturbance. They carry information from regions that light cannot easily escape, including the immediate surroundings of merging black holes. They also reveal objects that may emit almost no light at all. Space becomes audible only as an analogy, yet waveforms can be shifted into the range of hearing, turning changing frequency into a brief tone. Multiple detectors are essential. A real gravitational wave reaches observatories at slightly different times and produces related patterns. Local noise rarely matches across widely separated instruments. Comparing signals confirms that an event is cosmic and narrows its direction. While additional observatories improve triangulation, a network can identify regions of the sky quickly enough for telescopes to search for accompanying light. This coordination becomes especially powerful when neutron stars collide. Such mergers produce gravitational waves and can also generate bursts of high-energy radiation, glowing debris, and newly formed heavy elements. Observing one event through several kinds of messenger creates a fuller account than any single signal can provide. Space-time, light, particles, and matter all carry different parts of the same history. The detectors also test gravity under extreme conditions. General relativity has survived every confirmed gravitational wave observation, including the violent merger of compact objects. The shapes of the signals match numerical calculations based on Einstein's equations with remarkable accuracy. Still, each detection offers a chance to search for small departures, unexpected echoes, unusual polarizations, altered propagation speeds, or mismatched ring-down patterns could point toward new physics. So far, no decisive contradiction has emerged. The absence of such a contradiction is itself informative, narrowing the space in which alternative theories can hide. Individual mergers also build a broader map showing how often black holes collide, how massive they are, and how they may have formed. Their masses and spins preserve evidence of formation, evolution, and cosmic history. Future instruments may listen at different frequencies and across much greater distances. Ground-based observatories are sensitive to rapid waves from compact mergers. Space-based interferometers could follow slower waves from massive black holes and long-lived binary systems. Timing networks that monitor pulsars may detect even lower frequency ripples, produced by pairs of enormous black holes moving gradually toward collision. Together, these methods would cover a broad gravitational spectrum, revealing a universe in continuous motion. Beneath them all lies the same delicate principle light compares two paths. Quantum fluctuations set a limit, and a passing wave changes the geometry by an almost unthinkable amount. The detection of gravitational waves is often described as a triumph of relativity, and it is also a triumph of quantum control. Without coherent lasers, stabilized frequencies, photon-sensitive detectors, and methods for reshaping quantum noise, the ripples remain hidden. The largest collisions in the universe become measurable only because the smallest units of light can be organized with extreme care. At that meeting point, black holes and photons share one instrument. Space-time trembles across immense distances, and quantum light records the change. The event may begin in darkness billions of years ago, but its final trace appears as a faint failure of cancellation inside a silent detector, where almost nothing becomes enough to reveal the motion of the universe. Entanglement begins when two quantum systems can no longer be described independently. They may separate in space, pass through different instruments, and arrive at detectors far apart, yet their properties remain joined within one shared state. A measurement on one side reveals a result that is correlated with the result found on the other. The pattern can be stronger than any ordinary agreement produced by hidden instructions carried in advance. Distance does not erase the connection, but neither does the effect allow a message to travel faster than light. Entanglement therefore occupies an unusual place between connection and separation. It binds outcomes together without providing a visible signal moving between them, and it forces physics to reconsider what it means for distant objects to possess their own independent realities. A simple analogy begins with pairs of coins prepared so that their first flips always agree. One coin may be carried across a room while the other remains on a table. If each pair always produces matching results, the obvious explanation is that both coins were programmed in advance. Each carries hidden information telling it which face to show. Classical systems can create strong correlations in this way. Quantum entanglement differs because the observed correlations cannot be reproduced by any local model in which each particle carries a complete set of predetermined answers. Entangled particles can be tested along several possible settings, such as different directions of polarization or spin. If each particle merely carries hidden instructions, then the combined statistics must obey certain limits. Bell inequalities express those limits. Quantum mechanics predicts that entangled systems can violate those inequalities. experiments repeatedly confirm the quantum prediction. The particles produce correlations stronger than local hidden instructions can explain. This result does not reveal a simple signal crossing the distance. It reveals that the classical assumptions used to imagine separate objects are incomplete. Bell's theorem depends on several ideas that feel natural in everyday life. One is locality, the principle that an event cannot be influenced instantly by a distant choice. Another is that measurement outcomes reflect properties already possessed by the systems. A third is that experimenters can choose their settings independently of hidden features of the particles. The observed violations show that these assumptions cannot all remain true in the same classical form. Some interpretations abandon predetermined values. Others accept non-local connections within the underlying theory. Still others question how independence and causation should be described at the quantum level. Entangled particles are created whenever quantum processes link their possible states. A source may produce two photons whose polarizations are correlated. Two atoms may interact and leave with connected spins. A particle may decay into a pair whose combined properties obey conservation laws. The resulting state does not assign each member a complete individual description. Instead, it specifies the relation between them. The pair may have a definite total spin even though neither particle has a definite spin along a chosen direction before measurement. When one is measured, an outcome appears. A measurement of the other, using a matching setting, yields the correlated result predicted by the shared state. The relation is definite even when the separate properties are not. Everyday thought begins with objects and then adds relationships between them. Quantum mechanics can reverse that order. The relationship may be fully defined while the individual properties remain unresolved. The pair behaves as one quantum object spread across space. Separation changes the location of its parts but does not necessarily divide the state into independent pieces. The mathematical description belongs to the whole. This holism does not mean that the particles remain connected by an invisible wire. It means that the complete information cannot be divided into separate local accounts without losing the correlations the theory predicts. Each local outcome remains random. A scientist examining one particle cannot control whether the result will be one value or another. The distant partner's result is correlated, but that correlation becomes visible only after ordinary communication allows the two records to be compared. Because no chosen message can be encoded in the random outcome. Entanglement does not permit faster-than-light communication. Relativity's limit on signals remains intact. The strangeness lies not in sending information instantly, but in the way the joint state produces coordinated statistics without a classical mechanism unfolding through the space between the detectors. Einstein objects to this structure because it appears to threaten the independence of distant reality. Along with Boris Podolsky and Nathan Rosen, he argues that if quantum mechanics allows a measurement here to predict a distant result with certainty, then the distant property should already exist. If the theory does not include that property before measurement, perhaps the theory is incomplete. The argument is designed to defend a deeper reality with local causes. Bell later transforms this philosophical concern into an experimental question. By deriving limits for local hidden variable theories, he shows that nature can distinguish between classical completeness and quantum entanglement. The laboratory results favor the quantum correlations. The world does not preserve locality and predetermined properties in the straightforward combination Einstein hopes to retain. Even so, entanglement is fragile. Interaction with the environment spreads the shared state into surrounding systems, producing decoherence, stray photons, thermal motion, vibration, and imperfect control can destroy the correlations needed for a useful experiment. Creating entanglement is therefore only the first step. The systems must be isolated, transported, manipulated, and measured before environmental noise overwhelms the delicate phase relationships. Photons are valuable because they interact weakly with their surroundings and can travel long distances. Atoms and superconducting circuits are easier to store and manipulate, but often require extreme cooling and shielding. Entanglement has moved from foundational debate into practical science. In quantum cryptography, correlations can reveal whether an unwanted observer has disturbed a communication channel. The security can rest partly on physical principles rather than only on computational difficulty. In quantum teleportation, an unknown quantum state can be transferred from one system to another using shared entanglement and an ordinary classical message. No matter or energy disappears from one place and reappears elsewhere, and no information travels faster than light. The original state is destroyed by measurement, while the distant system is transformed into the corresponding state after the classical information arrives. The process shows that quantum information belongs to relationships as much as to individual particles. Quantum repeaters may eventually extend entanglement across large networks. Ordinary optical signals weaken as they travel through fiber, and direct amplification would disturb unknown quantum states. A repeater instead creates entanglement across shorter segments, stores the states in quantum memories, and connects them through a process called entanglement swapping. In that process, measurements performed on intermediate particles can entangle systems that have never interacted directly. The final connection is built step by step, not by sending one fragile particle across the entire distance. Such networks remain difficult because memories lose coherence and operations introduce errors. But the principle points toward a quantum internet designed for secure communication, distributed sensing, and linked quantum processors. Entanglement also improves measurement. Multiple atoms or photons can share a quantum state so that their collective response reveals a phase or frequency more precisely than independent particles could. Atomic clocks, magnetic sensors, and gravitational wave detectors can use such correlations to push beyond ordinary statistical limits. Squeezed light is closely related to this idea, redistributing quantum uncertainty among collective properties of the field. In these instruments, entanglement is not merely evidence of strangeness. It becomes a resource, something that can be created, consumed, degraded, and measured. The language of quantum information makes this resource easier to classify, even while its underlying meaning remains unsettled. The deepest implication is not that distant particles whisper across space. It is that separateness may not be fundamental in the way classical physics assumes. Two systems can occupy different locations while belonging to one indivisible state. Their local outcomes remain random, yet their shared pattern is exact. Space determines where measurements occur and limits how signals travel, but it does not necessarily divide quantum reality into independent pieces. Entanglement suggests that the universe is organized not only through objects and fields at points, but through correlations that belong to wholes. The connection leaves no visible thread and carries no controllable message, yet it survives every careful test. Across empty distance, the particles remain part of one description, and the meaning of that unity remains among the quietest and most persistent mysteries in physics. A quantum computer begins with a strange promise. Instead of forcing every unit of information into one definite state at a time, it uses physical systems that can remain in superpositions, become entangled, and interfere. These features allow certain calculations to be arranged in ways that have no direct classical equivalent. The promise is not that every problem becomes easy, nor that ordinary computers become obsolete. For some carefully chosen tasks, the structure of quantum mechanics may allow information to be processed through patterns of possibility that a classical machine cannot efficiently reproduce. At the center of this idea is the qubit, the quantum counterpart of the classical bit. A classical bit holds one of two values. It is either 0 or 1. A qubit can also be measured as 0 or 1, but before measurement its state may be a superposition of both possibilities. The state includes amplitudes that determine the probability of each result, along with a relative phase that controls how the possibilities interfere. This phase is one of the main resources of quantum computation. A useful algorithm arranges the evolution of many amplitudes so that paths leading toward the desired result reinforce one another while paths leading toward incorrect results cancel. The final measurement still produces an ordinary string of zeros and ones, but the probabilities have been shaped by a process unfolding in quantum state space. A single qubit offers only a small stage for this behavior. The deeper power appears when several qubits become entangled. Two entangled qubits cannot always be described as separate objects with independent states. Their information belongs to the pair. With each additional qubit, the mathematical space of possible joint states grows rapidly. A register of many qubits can carry a pattern of amplitudes across an enormous number of possible configurations. This does not mean that a quantum computer calculates every answer in parallel and then reads them all. Measurement returns only one outcome. Most hidden amplitudes cannot be inspected directly. The art of quantum algorithms is to manipulate the state so that useful global properties become visible in the final statistics. Without interference, the vast state space would remain inaccessible. Without entanglement, many of the strongest quantum correlations would disappear. A quantum program is built from gates, physical operations that rotate qubit states, change their phases, or entangle them with other qubits. These gates play a role similar to logical operations in classical computing, but they act on amplitudes rather than on definite values alone. A sequence of gates forms a circuit. The circuit begins by preparing the qubits, guides them through controlled evolution, and ends with measurement. Because the outcome is probabilistic, the same circuit is often run many times. The distribution of results is then analyzed. A successful algorithm arranges that the correct structure appears often enough to be identified. The best-known examples show why quantum computing inspires such interest. One algorithm can factor certain large numbers far more efficiently than the best-known classical methods, at least in principle. This matters because some encryption systems rely on the practical difficulty of that task. Another algorithm can search an unstructured collection with fewer steps than a classical procedure requires. Quantum simulation may be even more natural. Molecules, materials, and chemical reactions are quantum systems. Their states grow too complex for ordinary computers to track exactly as the number of particles increases. A controlled quantum device could imitate those systems using one quantum system to represent another. This could help study catalysts, batteries, medicines, and materials whose behavior depends on delicate interactions among electrons and nuclei. Yet the same laws that give quantum computers their promise also make them fragile. A useful computation requires qubits to remain coherent while gates are applied. Heat, vibration, stray electromagnetic fields, imperfect control pulses, and unwanted interactions can disturb the state. A qubit may lose phase information, change value, or become entangled with the environment instead of with the intended parts of the processor. This process is decoherence, the same mechanism that helps explain why large objects appear classical. In a quantum computer, decoherence is a practical enemy. The machine must preserve precisely the kind of fragile superposition that the surrounding world constantly destroys. Different hardware platforms attempt to solve this problem in different ways. Superconducting circuits use tiny electrical currents flowing through structures cooled near absolute zero. Trapped ions use charged atoms suspended by electromagnetic fields and controlled with lasers. Neutral atoms can be arranged in optical traps and linked through carefully chosen interactions. Photonic systems encode qubits in properties of light. Semiconductor devices attempt to use electron spins or related states within solid materials. Each approach offers advantages and costs. Some allow fast gates but lose coherence quickly. Some preserve states for longer but operate more slowly. No single design has yet settled the architecture of a large, fault-tolerant quantum computer. The word fault-tolerant is essential. Classical computers also make errors, but their bits are stable enough that simple redundancy can protect information. Quantum information cannot be copied freely because of the no-cloning principle, and direct measurement destroys the superposition being protected. Quantum error correction therefore works indirectly. A logical qubit is spread across many physical qubits in an entangled code. Carefully designed measurements reveal whether certain errors have occurred without revealing the encoded quantum information itself. Corrective operations can then restore the logical state. This method is one of the most remarkable achievements in quantum information, but it demands a heavy price. One reliable logical qubit may require many physical qubits, and every gate measurement and connection must remain below a strict error threshold. Building a useful machine may therefore require vast improvements in control, fabrication, calibration, and software. Current devices operate in a noisy intermediate regime. They contain enough qubits to perform interesting experiments, but not enough reliable error correction to sustain very long calculations. Their outputs must be interpreted with care. Noise can imitate structure. Small demonstrations can depend heavily on the details of the comparison with classical methods. A task may appear difficult for one classical algorithm while a better classical method remains undiscovered. Claims of quantum advantage therefore require precise definitions. The question is whether a quantum processor performs a meaningful task faster, more accurately, or with fewer resources than the best practical classical alternative. This boundary keeps moving because classical computing also improves. Quantum machines are unlikely to replace ordinary computers for writing documents, displaying images, storing records, or running everyday applications. Classical processors are already efficient for those tasks. The more likely future is hybrid. Classical computers prepare data, control hardware, optimize parameters, and interpret results, while quantum processors handle specific subproblems suited to quantum structure. A quantum device may function more like a specialized accelerator than a universal replacement. Even then, its value depends on finding problems where the advantage survives the cost of error correction, data loading, and repeated measurement. Theoretical speed does not automatically become practical usefulness. Quantum computing also changes the meaning of information. In classical theory, information is treated abstractly, as bits that can be copied, stored, and transmitted without changing their logical identity. Quantum information is inseparable from physical law. It cannot be cloned arbitrarily. Measurement alters it. Entanglement can distribute it across systems so that no single part contains the whole. These rules create limits, but they also create resources. Teleportation transfers states using entanglement and classical communication. Quantum cryptography can reveal certain forms of interception. Quantum error correction protects delicate states by encoding them into larger patterns. Computation becomes one branch of a broader science, concerned with how nature stores and transforms possibility. The uncertainty surrounding the field reflects the early stage of learning how to engineer a new physical language. The mathematical principles are established, yet the scale of useful machines, the best hardware, the most valuable algorithms, and the timeline of practical impact remain unresolved. Some expectations may prove too ambitious. Some applications may remain narrow. Others may emerge from directions not yet obvious. The machine itself sits at a boundary between control and noise, between elegant theory and stubborn material reality. Every qubit must be protected from the world, while still being connected to other qubits, manipulated by external fields, and measured at the end. Too much isolation makes computation impossible. Too much interaction destroys the state. The entire device survives within that narrow balance. In this sense, a quantum computer is not merely a faster calculator. It is a controlled experiment in maintaining an alternative form of physical order. It asks matter to preserve superposition, sustain entanglement, and guide interference through a long sequence of operations without surrendering those patterns to the environment. Success would not remove the mystery of quantum mechanics. It would place the mystery into service. The machine would compute by using the same unresolved features that make the theory difficult to interpret, turning possibility, correlation, and uncertainty into a technology whose final limits are still unknown. A black hole seems to represent the triumph of gravity over everything else. Matter falls inward, light cannot return, and the boundary known as the event horizon divides the visible universe from a region that no signal can escape. Classical general relativity describes this object with severe simplicity. From far away, a settled black hole is characterized mainly by its mass, rotation, and electric charge. The details of the matter that formed it disappear from view. A star may collapse with oceans of internal structure and countless particles, yet the final black hole presents only a few measurable properties. In the classical picture, the horizon is a one-way surface, and the darkness can last forever. Quantum physics unsettles that picture. It does not begin by sending a particle outward from inside the horizon. Nothing in Hawking's calculation requires matter to climb back through the boundary. The effect arises because quantum fields do not become silent in empty space. Even a vacuum is not a simple absence. Fields remain present, and their lowest energy states contain fluctuations shaped by the geometry around them. Near a black hole, the distinction between particles and empty space depends on the observer and on how the field evolves across curved space-time. A state that appears empty in the distant past does not necessarily appear empty in the distant future. The changing gravitational environment alters what counts as a particle, and a faraway observer detects a faint thermal flux. The black hole behaves as though it possesses a temperature. This result is often described through pairs of particles appearing near the horizon, with one falling inward while the other escapes. The picture offers intuition, but it is only a rough metaphor. Hawking radiation is more accurately understood through quantum field theory in curved space-time. The horizon alters the relationship between field modes in different regions. When those modes are compared between the past and future, the vacuum no longer remains empty for every observer. Radiation appears at infinity with a nearly thermal spectrum. The black hole loses energy because the escaping radiation carries energy away. Since mass and energy are equivalent, its mass decreases. Gravity, once imagined as the perfect captor, becomes linked to a slow process of release. The temperature of a black hole is inversely related to its mass. A large black hole is colder than a small one. Stellar mass and supermassive black holes have temperatures far below the surrounding cosmic environment. At present, they absorb more energy than they emit. The afterglow of the early universe, starlight, gas, and other radiation continue to feed them. Only in a much older and emptier cosmos, after the environment cools below their faint temperature, do they begin to lose mass faster than they gain it. The evaporation is then extraordinarily slow. A black hole with the mass of a star survives for a span vastly longer than the current age of the universe. a supermassive black hole lasts longer still. The process becomes rapid only near the end, when the mass has fallen and the temperature has risen. The final stage remains uncertain because the curvature and energy approach a regime where quantum gravity should become important. Hawking's result changes the meaning of a horizon. In classical relativity, a black hole has an area but no ordinary temperature. Thermodynamics concerns heat, entropy, and the statistics of many microscopic states. A black hole appears too simple to belong to that world. Yet earlier work shows that the area of an event horizon behaves like entropy. In ordinary processes, the total horizon area does not decrease. Matter falling inward increases it. The resemblance becomes more than formal when quantum effects give the black hole a temperature. Temperature and entropy belong together through thermodynamics. The entropy of a black hole turns out to be proportional to the area of its horizon rather than its volume. This is a profound clue. It suggests that the hidden information associated with the black hole may be counted on a surface. A region of space seems able to store physical information in a way that scales with its boundary. From this clue grows the holographic principle, the idea that the full description of a volume may be encoded by degrees of freedom on a lower dimensional boundary. The principle is not a simple claim that the universe is an illusion. It is a statement about how information, gravity, and geometry may be related at the deepest level. Black holes force this possibility because their entropy is enormous and follows the area law with remarkable precision. The horizon appears less like an empty edge and more like a ledger whose microscopic entries remain unknown. The greatest difficulty arrives when the black hole evaporates. Matter that falls inward can carry detailed quantum information. A book, a star, or a cloud of particles is not defined only by total mass and charge. Its quantum state contains correlations and phases. Ordinary quantum theory says that information is preserved through time. A pure quantum state evolves into another pure state, even when the information becomes scrambled beyond practical recovery. Hawking radiation, however, appears thermal. Thermal radiation is described only by broad properties such as temperature and carries no obvious record of the detailed state of the material that formed the black hole. If the black hole evaporates completely and the radiation remains perfectly thermal, the original information seems to vanish from the universe. This is the black hole information paradox. The paradox is not about the destruction of an ordinary message alone. It threatens the consistency of quantum mechanics. If pure states can become mixed states through black hole evaporation, then the usual rule of unitary evolution fails. Probabilities may no longer remain consistent through time, and the predictive structure of the theory changes. General relativity suggests that information can disappear behind a horizon and end at a singularity. Quantum mechanics insist that information must survive. Both theories are extraordinarily successful within their own domains, but the evaporating black hole places them in direct conflict. The paradox, therefore, becomes a test of any future theory that unites gravity with quantum physics. Several possible resolutions compete. The information may escape through subtle correlations in Hawking radiation, so complex that the radiation looks thermal when examined coarsely, but remains globally pure. The black hole may leave behind a tiny remnant that stores the information, though such remnants raise questions about how a small object can contain an enormous number of states. Information may emerge only at the final stage, when unknown quantum gravitational effects dominate. Some ideas alter the structure of the horizon itself. Others propose that the interior is encoded non-locally in the radiation or in boundary degrees of freedom. Each possibility preserves part of established physics while placing pressure on another part. Modern approaches increasingly suggest that the radiation does carry information. Calculations in simplified models and holographic theories produce an entropy curve that rises and then falls, As expected, if the final radiation is pure, early in evaporation, the radiation appears increasingly entangled with the remaining black hole. After a certain point, new radiation must begin to purify the earlier radiation. This behavior matches unitarity, but creates a sharp puzzle about how the correlations are arranged across the horizon. A late Hawking quantum seems required to be entangled both with an interior partner and with earlier radiation. Quantum mechanics does not permit unlimited sharing of that kind. The conflict leads to proposals as extreme as a firewall, a region of violent high-energy physics at the horizon that breaks the smooth passage predicted by relativity. The horizon, once thought locally uneventful for a falling observer, becomes a site where fundamental principles collide. No observation has yet detected Hawking radiation from an astrophysical black hole. The predicted signal is far too cold and faint against the surrounding universe. Laboratory analogues can imitate aspects of horizons in fluids, optical systems, or other media, and some display radiation-like behavior, but they do not reproduce every feature of gravity. The original prediction remains theoretical, supported by the union of quantum field theory, relativity, and thermodynamics. Its power comes from linking frameworks developed for different scales. A law of heat becomes a law of horizons, a quantum vacuum becomes a source of radiation, a black hole becomes an object with temperature, entropy, and a possible lifetime. The largest gravitational structures are challenged by the smallest fluctuations of fields. Over almost unimaginable spans, the horizon shrinks. The black hole grows hotter, the radiation strengthens, and the object that once seemed like the final prison of matter approaches an uncertain end. What remains is not merely a question about black holes. It is a question about whether space-time itself is fundamental, whether information is written on boundaries, and whether gravity emerges from a deeper quantum structure. At the edge of darkness, the smallest physics does not simply survive the strongest gravity. It begins to rewrite what a black hole is. Quantum theory stands as the most accurate framework ever created for describing matter and light, yet its central objects remain strangely difficult to interpret. The equations predict the outcomes of experiments with unmatched precision. They explain atoms, chemistry, semiconductors, lasers, superconductors, nuclear processes, and much of the structure that makes stars and planets possible. Still, the theory does not provide one universally accepted picture of what exists beneath those predictions. Its mathematics is clear, its meaning is divided. The wave function sits at the center of that division. It evolves according to exact rules and contains the amplitudes from which probabilities are calculated. It can spread across possible positions, combine different energies, and entangle distant systems into one state. Yet physicists continue to disagree about whether the wave function is a real physical entity, a description of knowledge, a catalogue of expectations, or a shadow cast by a deeper theory. The disagreement is not caused by imprecise experiments. It survives because several interpretations reproduce the same observed results while describing radically different realities. In one account, the wave function collapses when a measurement occurs. Possibilities become one fact through a genuinely random event. In another, collapse never happens. The universal state continues smoothly, and every allowed outcome persists within a separate branch. In another, particles possess definite positions, while a guiding wave directs their motion through a non-local structure. In still others, the quantum state represents relationships, information, or the expectations of an agent rather than an object existing in isolation. Each interpretation preserves the successful calculations. Each places the mystery in a different location. Collapse theory must explain what triggers collapse and why it has escaped detection. Branching theories must explain how probability arises when every outcome occurs. Hidden variable theories must accept forms of non-locality that classical intuition resists. Informational approaches must explain what physical world gives rise to the experiences and records being organized. The same experiment can therefore be surrounded by incompatible stories, all quiet beneath the same numerical prediction. The measurement problem remains the most visible sign of this incompleteness of meaning. A quantum state evolves as a superposition, then an instrument records one outcome. Decoherence explains how interference between macroscopic alternatives becomes inaccessible as information spreads into the environment. It explains why classical records are stable and why large objects do not display obvious superpositions. Yet decoherence does not uniquely select one result from the complete state. It shows how branches cease to interfere. Not why one branch becomes the single experienced world, unless an interpretation adds further structure. The apparent simplicity of a detector click therefore conceals the unresolved passage from mathematical possibility to physical fact. Another mystery concerns the boundary between the quantum and classical worlds. No fundamental scale has been found where quantum laws suddenly stop. Molecules, electrical currents, mechanical resonators, and increasingly large systems can display superposition or entanglement when sufficiently isolated. Classical behavior appears to emerge through interaction, complexity, and the loss of accessible phase information. Yet emergence is not the same as replacement. The large world remains built from quantum ingredients. Its solidity, definiteness, and continuity arise from a deeper description in which properties can be indefinite and alternatives can interfere. The familiar world may therefore be less fundamental than the relations and amplitudes beneath it. Quantum field theory deepens this shift. In that framework, particles are not the most basic objects. They are excitations of fields extending throughout space. An electron is a stable excitation of the electron field. A photon is an excitation of the electromagnetic field. Empty space is the lowest energy state of those fields, not a true absence. Vacuum fluctuations influence measurable phenomena, and forces can be understood through field interactions. Yet quantum field theory contains infinities that must be controlled through renormalization, a procedure that connects measurable quantities to underlying parameters. The method works with extraordinary success, but it also hints that current descriptions may be effective rather than final. They may capture the behavior of nature across accessible scales while hiding a deeper structure at distances far smaller than any experiment can yet probe. Gravity makes that possibility unavoidable. General relativity describes gravity as the curvature of space-time, while quantum theory describes matter and forces through states, fields, and probabilities. Each framework succeeds in its own domain. Together, they resist a complete union. At ordinary energies, quantum fields can be studied on a curved background, near singularities, inside the earliest moments of the universe, or during the final evaporation of a black hole. The background itself must become quantum. Space and time can no longer remain fixed stages. Their geometry may fluctuate, become entangled, or emerge from more fundamental degrees of freedom. No experimentally confirmed theory yet describes this regime. String theory, loop quantum gravity, causal structures, holographic models, and other approaches offer different possibilities, but none has gained decisive empirical support. The absence of a tested quantum theory of gravity leaves some of the most basic questions open. Is space continuous, or built from discrete units? Does time exist fundamentally, or does it emerge from correlations and change? Are black hole interiors ordinary regions, encoded surfaces, or signs that geometry itself is incomplete? Does the universe begin with a singular boundary, a quantum transition, or a state in which the idea of before has no meaning? These are not decorative mysteries added to a finished theory. They appear where the two strongest foundations of modern physics meet and fail to fit smoothly together. The values of nature's constants create another layer of uncertainty. The masses of particles, the strengths of forces, and the pattern of generations are measured with precision, but the established theory does not explain all of them from first principles. The Standard Model organizes known particles and interactions with remarkable success, yet it includes many values inserted from experiment. It does not identify the nature of dark matter, explain why matter dominates antimatter, or incorporate gravity. Neutrinos possess masses that require an extension of its simplest form. The vacuum energy predicted by quantum fields appears vastly larger than the dark energy inferred from cosmic expansion. This mismatch is among the deepest numerical tensions in physics. It suggests that the connection between quantum vacuum, gravity, and cosmology remains profoundly misunderstood. Even causality becomes subtle. Quantum theory preserves the rule that controllable information cannot travel faster than light. Yet entanglement produces correlations that cannot be explained through local predetermined properties. The world respects relativistic signaling while refusing a simple local account of separate objects. This may indicate that locality itself is emergent, arising from a deeper network of quantum relationships. In some theories inspired by holography, patterns of entanglement help build the geometry of space. Distance may reflect how strongly regions are connected within a quantum state. Space could then be less like an empty container and more like an expression of information woven into a larger whole. These ideas remain theoretical, but they point toward a reversal of the familiar order. Matter may not occupy space at the deepest level. Space may emerge from the way quantum information is organized. The mystery behind everything is therefore not one hidden particle or one missing equation. It is the unresolved meaning of the framework that already explains so much. Quantum mechanics does not fail where it becomes mysterious. It succeeds so completely that the mystery can no longer be dismissed as a temporary error. The probabilities work. The interference appears. Entanglement survives distance. Atomic transitions keep time. Lasers measure space-time. Black holes acquire temperature. Devices built from these principles operate across the modern world. Yet beneath every success remains the question of what the theory is saying reality actually is. Perhaps a future experiment separates the interpretations. Perhaps a quantum theory of gravity reveals that wave functions, particles, space, and time emerge from a deeper principle. Perhaps the present formalism remains complete, while human intuition slowly adapts to a world that cannot be reduced to classical pictures. For now, the theory ends where its accuracy is greatest, not in confusion, but in disciplined uncertainty. Everything visible rests upon quantum rules, while the nature of those rules remains partly concealed. The universe behaves as though possibility is real, relationship is fundamental, and definite facts rise from a structure that no single interpretation has fully claimed. At the deepest level currently known, reality is not silent because nothing is there. It is silent because the mathematics speaks more clearly than any image made to contain it.